I guess we'll get started again this afternoon at 3 o'clock. The entire faculty will be meeting with the administration at Appalachian State to make some plans about what's going to happen this fall and try and figure things out. Just know that we are doing our absolute best that we can to have you as students back here safely. Everybody wants to be back to normal as fast as possible. Hopefully, we can manage that and all the things that we need to for that. Um, let's talk some more chemistry. Just reminding you that if you have any questions, feel free to use the group chat in Zoom. I can see that. If you have any questions at all. Let's take a look at some more chemistry. I want to, by the end of the day, work through all of these reactions with alkenes. And what's nice about this is the stuff that we're doing now, when we go to two double bonds, it's not going to necessarily mean that we're doing something outrageously different. And so the work, if we do good, solid, foundational work right now, then when we move to things with two double bonds, it's not going to be a huge stretch for what we're doing. So let's take a look. I want to talk about this right here, radical reaction right here, and this reaction right here, this BH3THF over sodium hydroxide and HOOH. Most importantly, I want you to be able to recognize that when you see this, HOOH, that is going to create some differences in our chemistry. So the question that we are now going to move on to is, if we've said, here's in this bottom corner over here, if here's all the reactions that you have to know for the examination this Sunday. Well, if that's the case of all the reactions, then, and we've subcategorized some of these reactions, these addition reactions right here, as I work around this pinwheel, then the ones as your instructors that I want to draw your attention to then are the ones that, oh, I need that, that feature this HOOH thing. And so the question now is, what is peroxide? And I'm going to write ROOR or HOOH. What does peroxide do to a chemical reaction? And we live in a spoiler world, and so let's just get that part out of the way immediately. If I have a carbon residue with an alkene attached to it, we have spent time suggesting that addition of HBr to that alkene will result in the addition of hydrogen and bromine, such that the hydrogen will add to the carbon that already has the proton, and the bromine will add to the other carbon that was essentially the carbocation that preceded this. And so if that's the case, then what I'm going to suggest is that in the presence of peroxides, a completely different regiochemical product is obtained. Here we have addition, Markovnikov addition here, where the rich, this carbon here, the rich got richer. The carbon with the proton is the one that got the proton from the HBr. Then the presence of peroxide is enough such that the addition, the regiochemistry, is reversed. The hydrogen is now added to the carbon that was the one that had the bromine before, and the bromine went to the carbon that had the most hydrogens on it. This is anti-Markovnikov. Addition. This is also true when we looked at the addition of H3O plus or the addition of, what was that? What was the last one we just did? Yes, the mercuric acetate, HgOAc2, and water, followed by NaBH4, and we'll just do this as a 1 and this is a 2. We would expect to see Markovnikov addition, hydrogen OH, when we hydrate that double bond, when we add water across that double bond. But in the presence of peroxides, and let's see, what else are the requirements? NaOH, so this would be step 2, and this would be step 1, BH3.THF. We would expect to see addition or hydration of that water molecule such that the regiochemistry is reversed. And that's the important aspect of this. Mechanistically, I can absolutely go through a nice long-winded mechanism to explain why the hell this happens. We're not going to do that right now because it's not worth the time to explain something that is really ultimately a pattern recognition type instance. You have been taught a mechanism that can be applied to a lot of these addition type reactions. And then you just have to acknowledge that when you start to see HOOH, peroxide, the addition is going to take place in the opposite regiochemistry that you would expect. Over here, oxygen on this carbon, hydrogen on this carbon, the rich got richer. The opposite is true here. And so with these reactions, yeah, mechanistically, if we want to take some time during our Q&A session, someone can absolutely ask this question and I'd be happy to go over it. But when we're just looking at the reactions themselves, just memorize this. Hey, I have a pattern. HBr adds Markovnikov, but if I see peroxide, I'm going to get a separate type regiochemical product. And that's all you really need to know. It's just flipped. And so those cover those two other reactions. It becomes an important tool when we're trying to add different atoms to these bonds. We can, as synthetic chemists, control where those things are added, and that's something that'll come into play a little bit later for us. If we've talked about all of the common addition reactions, we've talked about the two instances where we can flip the regiochemistry of the reaction, that's great. Then all we have left to talk about for alkene reactions are the reduction reactions and then these really cool oxidation reactions that take place. And that's what I want to spend a little bit more time on now. There are really three types of reactions that you're going to see in organic chemistry: nucleophile, electrophile ones, oxidation, reduction ones, and then radical ones. And so let's take a look at some of these oxidations. We won't spend a whole lot of time right now talking about the mechanisms behind these reactions. I certainly can give you some little hints here and there, but when we look at some of these oxidation type reactions, is there a way that we can kind of utilize some pattern recognition to help you remember what functional group transformations actually take place? But we won't necessarily do a full-fledged proof with an electron pushing diagram. Let's take a look at one of these reactions. So I'll just write in our notes oxidation, and reduction type reactions. And I don't know formally if they all follow a strict definition of oxidation reactions, but the idea here is that you're absolutely increasing the number of oxygen atoms on these molecules. Let's take a look at one of these. Here's my carbon residue. And I want to take a look at the ozonolysis reaction, which is the one that my cursor is pointing to here, number 10. And that is the addition of O3 followed by dimethyl sulfide. And what we're going to end up producing is one aldehyde and another aldehyde, formaldehyde, as our product. So let's work through this. I first want to talk about what chemical transformation is taking place. Whenever I introduce a reaction to you, I want to cover all three of these areas. And so area number one for a new chemical reaction is the functional group transformation that occurs. And for this functional group transformation that occurs, we are starting with an alkene and we are making aldehydes. And I'm just going to put in parentheses ketones. Really important for you to memorize functional group names. They're on As You Learn. When I say these types of things, if you know what an aldehyde is, that's going to help because you have this arrangement of atoms. But so it's important to know you're going from one molecule to two molecules. But I'm just going to start that. There are instances where you only get one molecule. The best way to say this is you will be going from one alkene to two carbonyl-bearing molecules, two of these C double bond O's. So that's the functional group transformation that's taking place. What region of the molecule? So the question number two is regiochemistry. For that, that's pretty easy to keep track of. It's occurring on the same region of the molecule. The chemical transformations are occurring on the same region of the molecule in the products as the reactants. And then three, the stereochemistry. And for us in this reaction, we're winners here because the products we form are sp2 hybridized. And as a result, we don't need to worry about the chirality. Thank baby Jesus. And so for this reaction, we're looking at what is the transformation? I'm converting an alkene in the presence of ozone into these two functional carbonyls here, of which they're both aldehydes in this example. They could be ketones, and we'll go through examples of this during our Q&A tomorrow. But the idea here being that that you substitute in double bonded O's for this alkene. And if you look at the video instead of this, the notes here, the idea is if here's my carbon number one of my double bond, here's my carbon number two of my double bond, and the idea here is that that ozone is it's kind of like my head is going to just insert itself in between these two things and rip them apart. I don't have enough. Stand back. Rip those things apart and place oxygens in them. And so we will not go through a full-fledged mechanism of this reaction explaining where every single electron goes. We don't need to make that rigorous treatment to relay the idea in my mind that when I look at an alkene like this, and reacting that in the presence of O3 and then dimethyl sulfide, what I'm really thinking in my mind, without a mechanism, what I am thinking, even as an instructor, is that I am ripping, and I'm really exaggerating these things, but I am ripping this carbon away, and I'm ripping this bond in half and making this carbon move away. They're pulling on each other. They're pulling them apart. And as I do, then what I'm going to want to do is as I rip these things apart, and there's some really awesome chemistry that's taking place here, of which we really don't need to focus our whole time on. But as I rip these things apart, in my mind, I'm thinking, man, it'd be really cool then if I could insert some oxygen atoms, OXYGEN, in that space. And that's where these double bonded oxygens end up coming into play, is I've effectively ripped apart that double bond and then placed oxygens in between them. And so that's the idea there, is this ozonolysis. It actually goes through this. So here's the think part, and then reality. This really cool thing happens where these oxygen atoms, oh, time to expose yourself, because let's see if I actually remember this correctly. Oxygen. Oxygen. Did I do that right? Ha! Take that, grad school professor, in your face. Yeah, these oxygens actually insert themselves between these two carbons and actually do rip them apart. And so that's kind of what I'm envisioning here, is I'm pulling those things apart to place those double bonded O's in their place. And you'll notice that here in this example, I have molecule 1 and molecule number 2 here. But in the example over here, you'll see that you only get one molecule as a product, and that's because your alkene was attached. If I had, let's just do this. If I had carbon atoms that attached on other sides of that double bond, then those same arrangement would be keeping these molecules together like this, and you would end up with just one molecule if this was preferred. So linking here preserves those molecules, that keeps them tethered, so that if it's linked at two different places in the molecule and we rip apart that double bond, well, then there's something else tethering that molecule together. So I'm trying to give you the two instances. You won't always see two molecules formed if that double bond has been tethered to itself somewhere else in the molecule. So just be aware that you're not always generating two. That's why the example right over here in your textbook, number 10, only shows one molecule, because the thing was tethered in this ring. Here's that double bond, and we're going to rip that apart, but look at this nice carbon tether that works its way around to also keep that double bond connected, and so you'd end up with just one molecule. And so that's oxidation and reduction type reaction with ozone. Now let's take a look at the reaction when we have a carbon residue, and we're reacting that with 1OSO4, and then followed this by base, NaHSO4, H2O. Or another way of accomplishing this exact same transformation is to use potassium permanganate, KMnO4, and then you would end up producing a dialcohol compound, a diol. Di, two of them, alcohol, diol, and you're starting with an alkene. And much like the previous reaction, I'm going to kind of give this to you without a mechanistic proof to it, mainly because not a great one exists. There's some hand-wavy stuff that happens in a lot of these oxidation reactions. And that's not because we're stupid as organic chemists. It's because there's just a number of different possible pathways the reactions could go through. Just a quick sidebar, the addition reactions to alkenes were nice to kind of put in their subset because there's only really one pathway for the reaction to go through. When you get into oxidation reduction reactions, there's a number of different pathways that these molecules can undergo. And as a result of that, the mechanisms get a little bit dicey. And certainly plenty of research has gone in to show all the multiple pathways that could occur. Because there's so many, we're just not going to focus on it. But again, let's take a look. Functional group transformation. Well, that's the alkene double bond to two OHs attached to this molecule. And this is actually a really important reaction. I know you might see a double bond and hopefully you see two OHs, but as a medicinal chemist, this molecule right here probably doesn't have any solubility. This now with these two OHs on it are likely to have solubility in the body, so that's why we use this a lot for drug delivery. That's a functional group transformation that occurs. What about the regiochemistry of this reaction then? It looks like, and I'm just going to star this right here, it looks like the vast majority of the chemistry is going to take place on the same exact region of the molecule that we had the alkene on. And so the regiochemistry is the same as the alkene for all practical purposes. The last question when we look at a new reaction together that we're going to want to make sure artifact that we want to make sure to look for is the stereochemistry. And for this, especially at carbon 1, the carbon number 1 that I have denoted there, just like we'd seen before, it's highly likely that if the right example exists, that does become a chiral center, and then you'd have to denote that as making two possible products, the R and the S, of the two different enantiomers that would be formed. But yeah, stereochemistry could be an issue. Now, mechanistically, certainly, again, I told you there are aspects of this that I could show you, but the nice thing that I like to think about in an artifact that's so important with these types of reactions, both OHs are added to the same side of the molecule. So in an example where we have an alkene like this, and we've placed them under these oxidizing conditions described right here, both of those OHs are going to add at the exact same side of that molecule. We'll be looking at an example right over here where they occur on opposite sides, but how mechanistically, is there a way that we could explain this? Kind of like the old example that I just gave you where I thought about, let's rip this double bond apart and see what types of products we could make. Is there a nice, easy way to look at these reagents and think about what the heck is the transformation that's occurring? Thinking about this reaction, here is a pretty straightforward Lewis structure for KMnO4 and for osmium tetraoxide OSO4. If both of these things are going to react, in my mind, and mechanistically this is true, there's a lot of arrows all happening at once, but I kind of think of just like a stamp, like an old school actual stamp where you like put the thing in the ink and push down and then pick up and then push down to leave the imprint on the piece of paper. That stamp that occurs, it's kind of like that. If this thing is the stamp, here's my carbon residue, and here I am going to almost, in my mind, I'm thinking about like this MnO4 just coming straight down onto that double bond, and it's going to imprint two oxygens onto that double bond as OHs. That's kind of what I'm thinking in my mind, that this molecule is approaching, and it is going to deposit this oxygen here, this oxygen in here, and by virtue of the remaining reagents, that'll convert them into OHs. But that simultaneous stamping of the KMnO4 osmium tetraoxide onto that double bond, that stamping, that kind of explains how you're able to get one and the other on the same side of the molecule at the same time. Boom, both of them are delivered at the same time. You can't add one before the other, all concerted, all happening at once, and you're left with these oxygens that are attached that eventually become OHs through the remaining parts of that chemistry. And even though these aren't necessarily chiral, I'm adding the wedges here in this example to preserve the idea that those oxygens are both being implanted at the exact same time. And so that's why we get what's called syn addition. The syn, same side. The opposite would be anti-addition. That's the next example I'll do. But here you get same addition because really stamp. It's on, and then the reaction is pretty much over. Where is it? There it is. R, C, double bond O, 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 H. Two O, O, H right in a row. And then followed by acidulated water conditions, will produce a diol as well. So we're working in the same type of chemical transformation occurring, but in this example, so kind of give this a split right here. In this example, functional group transformation is the same. I've converted an alkene into a diol, so the transformation is the same. The regiochemistry still taking place on the same exact carbons. The stereochemistry, yikes, this carbon and sometimes this one are prone to potentially having stereochemical incidents if the example allows for that. And then taking it one step further, then this is added in an anti-fashion. And so all of a sudden, the stereochemistry, once we've figured out the stereochemistry with respect to the carbon atoms, we can ask how were those things added with respect to one another, since we're adding two of those things. And it appears like this was added in a manner where one oxygen was added first, and then once it's added, imposes a stereochemical steric type restraint that doesn't allow the second OH to add to the same side. It's going to want to and need to come in from an opposite angle in order for that reaction to take place. And so when we look at this, anti-addition here. So is there a nice trick that I could show you that that you could potentially use here to kind of at least remember how these reactants are a little bit different than the ones that you've seen before? Could at least help us figure out the mechanism for this. When we look at these peroxy acids, this is what this molecule is called, a peroxy acid. And that's the virtue of this two oxygens bonded to one another at the exact same time. Those peroxy acids, is there a way that we could look at this? And I'm trying to page through my textbook here to find a really good example of this, and I don't know if there's going to be one. There they are. Yeah, absolutely. Mechanistically, there is a moment that might help us remember what's happening here. I don't know if it's really the best, but the idea is that at some point during the reaction, so mini, we'll just write mini mechanism, kind of like a sidebar. At some point in this reaction, let me just lower this. We end up adding this whole molecule to this double bond, this whole entire peroxy acid, and some really wild chemistry happens after that. What I want to draw your attention to more so than anything is during this step right here. This is where we impart our first OH. And the idea is that this OH is added first. Therefore, any other OH must add from the opposite side. The opposite side of the molecule. And so the idea is just simple that when I've got this carbon residue, if I were to sight down this carbon-carbon bond, I would see the top half of that molecule occupied by all of this business. So if I were to sight down this carbon A to carbon B, kind of like a Newman projection where I just have carbon A right here, and then behind it is carbon B. At that point in time, I've got a bunch of stuff. All of this stuff right in here is occupying this portion of the molecule. That's this OH carbon thing. All of that stuff is occupying the top half of that molecule. And so what I'm just simply trying to say with a really terrible picture is that anything else will have to add from the bottom side. It's too sterically hindered up top to add anything else to that molecule. And because it's too sterically hindered, anything that we would have to add, an incoming OH in the end, would have to come from the opposite side of the molecule. And that's why in these examples here, you get anti-addition when we're using peroxy acids versus the stamping type mechanism of delivering two alcohols, which would occur when we use osmium tetraoxide or when we use KMNO4. And so both of those options produce syn addition. I know this is not like you didn't come to lecture to hear this really crappy explanation on this, but I don't want to go into a full-fledged 20-minute mechanism to just lose everybody when the core of this is a really straightforward idea that I can illustrate that you can then apply. Let's not try and muddy the waters per se with all these extra minutiae and details that are much more pertinent for an advanced OChem class when we can just focus on something really simple and accessible that you already get. I don't have to explain sterics to you. This stuff, and I'm going to do it anyways apparently, this stuff up here is sterically creating bulk, and so our other OH has to add the opposite side. It's not added at the same time in this mechanism, and so that's why you just get anti-hydroxylation. Then finally, last but not least, then is the reduction reaction, and that is taking a carbon residue and reacting that, I believe our notes say, in the presence of H2 and platinum. and you just add 2 hydrogens to that. This is a reduction reaction, and so first, the functional group transformation that occurs, we are going from an alkene to an alkane, completely saturating this. This is what you actually hear about this in the food industry quite often. These are your saturated fats, your hydrogenated oils. Those are taking alkenes and hydrogenating them with hydrogen in a similar reaction to produce a more stable shelf life product that is debatably bad for you, but it tastes so delicious. Addition of these hydrogens, this is actually a really fun reaction in organic chemistry. This is one of the few reactions where you have a huge propensity to blow the F up. I've done this reaction a number of times, have not exploded it, but it's a really fun reaction because you take a glass jar with a wall that's maybe this thick, so maybe like 2 inches thick, and you mix it with hydrogen gas, which Hindenburg isn't necessarily the most stable gas in the world, and then you add some platinum, and then you put this thing under pressure, like you pump it up like a car tire, and this apparatus that just rocks it back and forth. And so again, you have some really great requirements, right? Pressure, hydrogen gas, inside an explosive glass bottle. And this is how these reactions are conducted. There is no mechanism for this reaction. Even a well-researched one, there isn't necessarily a great way to look at this, except using my stamping model, the idea here. You will see in textbooks the surface of a platinum atom represented here with just the surface. Here's that platinum atom and its surface. When it's combined with hydrogen, the hydrogens, a very expensive reaction, you're using platinum. The hydrogens essentially interact and bond to the surface of that platinum, and here comes your incoming alkene. And again, we're going with the idea of like a docking station, a stamp. That alkene is going to come down, touch on the surface of that platinum, and up. It's going to rise back up, and you are left. Oh, that got out of control. There's no way to abort that. It is what it is. Hydrogen has been added. Your platinum surface now is devoid of that hydrogen. It will replenish as you continue to add more hydrogen to the surface, to the reaction mixture. But the idea is that here's your alkene, here's that surface of platinum, boom, pick up 2 hydrogens. I'm reduced, I'm moving on, the reaction is complete. And so that's the idea you can use for these reactions. We don't need to go through any sort of formal reaction mechanism for these reduction reactions. That covers everything. That covers absolutely everything with our reactions of alkenes. And so when we start to look then at this set of reactions that you have to memorize, we've talked about and tried to at least summarize some key points for every single one of these reactions. Whether you could use these reactions and have them follow the similar mechanism of an addition reaction, or are they these nice little thought pieces of ripping something apart or stamping something else, or sterics to explain the stereochemistry. Hopefully I've rationalized, and even in the worst one possible, how these reactions could take place. It becomes your job now to start to apply these reactions to the problems that are outlined in your unit study guide, and to also to memorize these, whether that it's note cards or whether or not it's just writing these things out on a sheet of paper like a psychopath, which is what I do because note cards don't work for me. I am going to post a video tonight. It's entitled Thinking About Memorizing. What a great name. But it's going to just give you some clues on how to make some really rich note cards for you, and how to memorize if you're going to write things down, and just memorize some key points. And so putting all of that together in a note card, I'm going to give you some instructions for that. So let's look ahead to, you can look ahead to having something that'll assist you then. Where do we go from here? Well, this is just going to be a teaser, and then we'll call it quits for today. If we can take an alkene and add HCl to that alkene to get a halogenated compound, if we can undergo that process, then we simply are moving on to the part where we ask the same question of adding HCl to an alkyne. If adding HCl to an alkene gives us a halogen, do we know enough to predict what would happen to an alkyne, two double bonds reacting with HCl? And we can spoil this by acknowledging that at least two equivalents of HCl would be necessary in order to complete that reaction, because we have two double bonds. Well, we have so much to memorize, because here's the alkenes, and here's addition of, let's just focus on reaction one, addition of HX to this alkene. If we look at the alkynes reaction, hey, here's addition of HX to an alkyne. And here's what happens if there's one equivalent of HX added. And here's what happens if there's an excess amount of HX added. You get two equivalents of HX added instead of one. And so what I'm trying to say is that we have a bunch of reactions that you have to memorize for the examination, but there is an immense amount of overlap. Here's one double bond reacting with one HX. If you understand that conceptually, it shouldn't be much harder than to say, hey, I've got two double bonds, and I can react it once, or I could react it twice. And if I'm doing my job for you, then you're going to start to see these similarities, and all of a sudden, HX is just a reagent. You're going to see two nucleophiles, two double bonds here, or two pi bonds rather, a triple bond, and you're just going to be thinking about how many iterations can this reaction undergo. And it's going to be our job to go through all of these reactions, just like I did today with alkenes, tomorrow with alkynes. But let's just take a look at how you can use what you already know to make predictions about how these reactions are going to take place. So if we know something about alkenes, can we make predictions about alkynes? And I'm going to walk through this quickly because we're going to pick up with this in more in depth here when we get back together tomorrow. But I want to just make a point. I have an alkyne. It's just a pi bond. We already know how pi bonds are going to behave. They're going to behave as nucleophiles. We've done this a bunch today. Here's our electrophile. We should expect to see addition of that hydrogen to that species leaving behind a positively charged carbon that's also double bonded to another carbon. Hey, look, here's our chlorine. We're just going to continue to play this game. Here's our nucleophile. Here's our electrophile. If I'm doing my job, I should be able to say this nucleophile will react with that electrophile. And look, by just simply knowing what we've learned today, we can make an honest guess about what would happen to an alkyne under similar conditions. There's one equivalent. If it was a nucleophile here, it's got to be a nucleophile over here. If it was an electrophile here, here's an electrophile. Again, it's going to behave like an electrophile. Again, we have nucleophilic attack, breakage of that HCl bond. Keep in mind, don't forget there's an implicit hydrogen right here. And so I've never shown that completely. It's hidden here, hidden here, hidden here, hidden here. But that doesn't change anything because here's the nucleophilic attack of the negatively charged nucleophile with the positively charged electrophile. Here's the beauty of a lot of the alkyne type reactions. Not a chiral center, not a chiral center. And so neither one of those carbons become chiral, and so we don't have to worry about stereochemistry here. Regiochemistry, we'll get into that stuff at a later date. It is 10:47 here, and I have run out of things to say. We've segued into the next section, which is alkynes, which we will pick up with tomorrow. So if you have any questions, I'll stick around on Zoom for a few more minutes. If you have any questions, please feel free to stick around and ask them. Once y'all are gone, I'm going to get on my bike and climb up to Elk Knob and suffer through that, and then you'll see me again for a video this evening, and then we'll be back for class tomorrow. So have a fantastic Monday wherever you are. Stay safe out there and drink lots of water. I'll stick around for questions.